Here we're going to prove L'Hopital's rule, so I'm going to remind you of what it says. If f and g are differentiable and we have limits that are both 0 or both infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x if the limit on the right hand side exists. Now, if you've watched the other videos in this section, you'll notice that in some cases we were looking at limits as x approached infinity. We'll look at that at the end of this, but for now we'll start looking at this proof. This proof uses a generalization of the mean value theorem, and so let's remind ourselves what the mean value theorem says. For f, a continuous function on the closed interval from a to b and differentiable on the open interval for a to b, there exists a c in between a and b such that f prime of c is equal to f of b minus f of a over b minus a, which is the average rate of change. And just to remind you of the mathematical shorthand, backwards uppercase E is there exists, the forward-facing curly-looking E is in, and the backwards-looking curly E is such that. The generalization is called Cauchy's mean value theorem, and it starts out the same way as the mean value theorem for f continuous on the closed interval, differentiable on open interval a to b, and g prime is not equal to 0 for all x in the interval from a to b, and that upside down uppercase A is for all. Then there exists a c in the open interval from a to b such that f prime of c divided by g prime of c is equal to f of b minus f of a divided by g of b minus g of a. I won't take the time to prove Cauchy's mean value theorem, but I'll say that it is proved by letting h of x equal f of x minus f of a minus the fraction f of b minus f of a divided by g of b minus g of a, all times, not all times, that fraction times g of x minus g of a, and using Rolle's theorem. If you want to see how something like that goes, I would recommend that you look in the earlier chapter where the mean value theorem is presented. Meanwhile, back to L'Hopital's rule. Assume that the limit as x approaches a of f of x is equal to 0, and that's also the value for the limit as x approaches a of g of x. Then we let L equal the limit as x approaches a of f prime of x divided by g prime of x. We define a function uppercase f of x to distinguish it from the lowercase f, and say it's equal to lowercase f of x if x does not equal a, and 0 if x does equal a. And we define a similar function for g, where uppercase g matches lowercase g as long as x is not a, and is 0 if x is a. Well, f and g, that is uppercase f and g, are continuous on the interval from a to x, that's the closed interval. The reason for that is because of how uppercase f and g are defined. If x is not a, uppercase f matches lowercase f, which has a limit of 0. So the limit for uppercase f as x approaches a is 0. And the function value as x, if x is a, is equal to 0. Therefore, f is continuous. Likewise for g. Differentiable because, again, they're based on f and g in their definitions. By Cauchy's mean value theorem, then, there exists a number y in the interval from a to x such that uppercase f prime of y divided by uppercase g prime of y is equal to f of x minus f of a divided by g of x minus g of a. But folks, f of a and g of a are 0 by definition. Therefore, f prime of y divided by g prime of y equals f of x divided by g of x. But since y is in an interval contained by a and x, as x approaches a, y also approaches a. This is represented from the positive side, so as x approaches a from the positive side, y approaches a from the positive side. So the limit as x approaches a from the positive side of lowercase f of x over g of x is equal to the limit as x approaches a from the positive side of uppercase f of x over uppercase g of x, which we've just shown is the same as the limit as y approaches a from the positive side of f prime of y over g prime of y, those being the uppercase values. And since those derivatives are equal to their lowercase counterparts, this is also equal to the limit as y approaches a from the positive side of lowercase f prime of y divided by lowercase g prime of y. We had originally said that that limit was called L, and what we have just shown is that L is equal to the limit as x approaches a from the positive side of f of x over g of x, the lowercase versions. A similar argument is used as x approaches a from the minus side, and this concludes the proof. Now, folks, this is for finite values of a. If a is infinite, then we make a substitution, let t equal 1 over x. Then t approaches 0 as x approaches infinity. We can then write that the limit as x approaches infinity of f of x over g of x is equal to the limit as t approaches 0 from the positive side of f of 1 over t divided by g of 1 over t, right? Just making that substitution in the argument and for the variable for the limit. And that equals, by L'Hopital's rule, for a being a finite number, the limit as t approaches 0 from the positive side of f prime of t times negative 1 over t squared divided by g prime of t times negative 1 over t squared by the chain rule. Of course, those 1 over t squareds, negative 1 over t squareds divide out, and we end up with this equals the limit as t approaches 0 from the positive side of f prime of 1 over t divided by g prime of 1 over t, which equals the limit as x approaches infinity of f prime of x divided by g prime of x. And so we've shown this time that the limit that started out with f of x over g of x as x approaches infinity equals the limit for the derivatives. And that justifies the work that we did for in situations in which x was approaching infinity or negative infinity.